Hello everyone, my name is Luhan. My presentation topic is SRLRF, fine-grained the root cause analysis and the prediction for compiler optimization defects. I will introduce 6 parts, including introduction, taxonomy, framework of our automatic prediction, experimental setup and results, and the conclusion. Section 1, Introduction. Compiler defects, especially optimization defects, pose significant threats to software systems. Diagnosing their root causes is crucial for efficient debugging. There only exist coarse-grained categories of compiler optimization defects, including miscomplication, crash, and performance. Such taxonomy provides limited assistance to developers in debugging. The challenges lie in, first, complex optimization interactions make it different to track and debug. Secondly, different optimization defects may lead to similar compiler symptoms, but their root cause is maybe completely different. So we would like to construct a systematic taxonomy for optimization defects in C compilers and realize automated category prediction. Section 2, Taxonomy. We use a data-driven approach to develop the root cause taxonomy of optimization defects in C compilers, including 3 steps: historical bug information, collection, manual analysis, and iterative refinement. Step 1. Historical bug information collection. The goal is to collect the historical bug data on GCC optimization defects and construct the correlation between bug reports and their corresponding debugging information. So we retrieve all commits related to tree optimization component from the GCC Git repository and pass the mapping relationship between bug IDs and multiple fixed fields from commits. Then we manually exclude fields that are not related to optimization. The final taxonomy is a 2-layer structure consisting of 8 major categories and 14 subcategories. This table shows our taxonomy, and more details can be found in our paper. Section 3, Framework. Based on the constructed root cause taxonomy, we propose SRLRF to automatically predict the root cause of compiler optimization defects, including 3 components: pre-processing, fine-tuning large language models, and stacking example learning. Pre-processing. The goal is to separate the code and the text within the bug report and embed them into a promote template to fully utilize the features of the code elements. We modified an open source tool called InfoZilla to extract C language code regions from text based on isoligned parsing method and regular expressions. And then we design a promote template and embed separate code and bug descriptions as imports for large language models. Fine-tuning large language models. We mainly use 2 models, RTA and Llama 3.1. RTA is a variant of BERT, specifically designed for automated software maintenance tasks such as bug priority and severity prediction. Llama 3.1 is a pre-trained and instruction-tuned generative model with strong understanding of code semantics and structure. The goal is to fine-tune large language models to generate soft labels for bug reports for subsequent stacking example learning. So we add a classification head at the end of RTA for 4 parameter fine-tuning. For Llama 3.1, we use LRA for parameter efficient fine-tuning. Stacking example learning. The goal is to take advantages of a domain-specific LLM and general-purpose LLM to enhance prediction performance. Firstly, we randomly divide the dataset into 5 folds. Secondly, we perform cross-validation for models on the first 4 datasets to generate soft labels and concatenate them to form the meta-features. Thirdly, we train the meta model using the above set of meta-features. Fourthly, we train the models on the 5th dataset and generate meta-features. Finally, we use the random forest trained in step 3 to evaluate the meta-features in step 4 and obtain the final predicted category. Section 4. Experimental setup. The dataset contains 5,573 bug reports. Product GCC component is tree optimization. Status is resolved. Time from March 2004 to June 2024. Compiler versions range from 3.4.0 to 14.0. We compare with 4 typical text classification approaches. SVM is a typical shallow machine learning approach. Fast text is a typical word embedding model. TextCN is a typical deep learning model. BERT is a typical pre-trained large language model. The evaluation method and metrics are accuracy, macro average, precision, recall, and F1 score. Section 5. Experimental results. RQ1. What is the performance of SRLRF in classifying bug reports into different root causes for GCC optimization components? We evaluate SRLRF and 4 typical text classification approaches in predicting the root cause categories of defect reports. The results show that SRLRF retrieves the overall accuracy of 63.11%, which is an improvement of 19.17% over SVM, 179.99% over fast text, 14.3% over TextCN, and 16.98% over BERT. RQ2. Whether separating code and text description in bug reports could boost the performance of SRLRF. We compare the original SRLRF against its variant, which does not separate code and text description in bug reports. The results show that without the pre-processing of bug reports, the accuracy of SRLRF drops by 1.62%. Macro average precision drops by 3.99%. Recall drops by 1.42%, and F1 score drops by 2.35%. RQ3. Whether combining the 2 basic models in the stacked ensemble learner is effective. We compare the original SRLRF with only using the single basic model RTA and Llama 3.1 to illustrate the benefits of combining them together in the stacking ensemble learning component. The results show that the overall accuracy of SRLRF is 63%, which outperforms the RTA and Llama 3.1 by 3.9% and 4.58%. Section 6. Conclusion. Problem. The existing classification standards are limited to describe the surface features and symptoms of the defects, and provide limited assistance to developers in debugging. We summarize the root causes of defects from historical bug debugging information and leverage a data-driven approach to construct a systematic taxonomy containing 8 root cause categories. Then we propose SRLRF to automatically analyze and predict the root causes for compiler optimization defects. Our approach achieves the accuracy of 63% and the precision of 60% and the recall of 54% and the F-score of 56%, which outperforms existing text classification methods. We open the source code and insights of this study to the public. This concludes my presentation. Thank you for your attention. If you are interested in any further details, please feel free to contact me.